This is Sleepy Space, a slow space story to help you fall asleep. On a clear night, far from city lights, you can see it, a pale band of light stretching across the darkness, the Milky Way. For thousands of years, humans looked up at that faint river of stars and imagined stories. Some saw it as a road between worlds. Others believed it was a trail left by gods or cosmic travelers. It felt distant, beautiful, and unreachable. What we did not know for most of our history was that we were inside it. The Milky Way is not something we observe from afar. It is our home. Our entire solar system, our sun, our planet, every star visible to the naked eye. All of it exists within this vast spiral of light, stretching more than 100,000 light years from edge to edge. And at its center, something waits. If you look toward the constellation Sagittarius, toward the densest region of that glowing band, you are looking inward. You're looking toward the heart of our galaxy. And there, roughly 26,000 light years away, lies an object unlike anything else in the Milky Way. Something massive, something invisible, something that should not exist according to everyday intuition. For most of human history, we had no idea it was there. When astronomers first aimed telescopes toward the galactic center, they found their view blocked. Not only by distance, though the distance is staggering, but by dust. Vast clouds of gas and microscopic particles fill the space between stars, absorbing and scattering visible light. Looking toward the center of the Milky Way with ordinary telescopes is like trying to see through thick fog. The harder you look, the less you see. For centuries, the core of our galaxy remained hidden, a mystery sealed behind darkness. That changed in the 20th century. As radio astronomy developed, scientists discovered that the universe emits light far beyond what human eyes can detect. Radio waves with wavelengths much longer than visible light can pass through dust almost unhindered. For the first time, astronomers could peer through the fog and observe the galactic center directly. What they found was unexpected. In the early 1970s, astronomers detected an intense radio source coming from the exact center of the Milky Way. They named it Sagittarius A, marking it as the primary radio source in the region of the sky. But as instruments improved, something more disturbing emerged. Within Sagittarius A, there was a point, a single, compact source. Bright, concentrated, extraordinarily energetic. They called it Sagittarius A star. This was not a nebula. It was not a cloud. It was not spread across space like most astronomical objects. Whatever this was, it was confined to a remarkably small region, astronomically speaking. Yet, it produced immense amounts of energy. The radio emissions told a story even before the object could be seen: the brightness of Sagittarius. A star varied over time. Sometimes it flared, sometimes it dimmed. These changes occurred over hours, sometimes even minutes, and that detail mattered. Light can only travel so far in a given time. If an object changes brightness across its entire surface in under an hour, then that surface cannot be larger than the distance light can cross in 60 minutes. The calculations place the emitting region at a size smaller than the orbit of Mercury. And yet, this tiny region sat at the gravitational center of the galaxy. Hundreds of billions of stars orbit this point. That was not coincidence. That was structure. As observations expanded beyond radio waves, the picture grew stranger. X-ray telescopes detected high-energy radiation from the same location. Infrared observatories capable of piercing through dust revealed a dense swarm of stars surrounding the invisible source. These stars were unlike those near our Sun. They were packed tightly together, moving at extraordinary speeds. Some completed orbits in just a few decades. Their paths bent sharply, whipped around an unseen center and curved back again. The only thing that could move stars that fast in such tight orbits was something incredibly massive. But there was nothing visible there. By the late 20th century, astronomers had established several facts. Something sat at the center of the Milky Way. Something compact enough to fit inside a planetary orbit. Something massive enough to dominate the motion of the entire galaxy. Something energetic enough to shine across the electromagnetic spectrum. And yet, it could not be seen directly. The evidence pointed toward a conclusion that once belonged only to theory. A type of object predicted by the equations of general relativity. An object where gravity becomes so intense that space and time themselves distort. A supermassive black hole. Not a hole in the ground, not a tunnel, but a region of space where matter has collapsed to such density that nothing, not even light, can escape. If this conclusion was correct, then at the heart of our galaxy lies an object containing millions of times the mass of the Sun, compressed into a region smaller than the distance between planets. An object that does not shine, but reveals itself by what it controls. Every star in the Milky Way, including our own Sun, moves in response to this invisible presence. It shapes the structure of the galaxy. It anchors the spiral arms. It defines the center around which everything else turns. And it has been there for billions of years, long before Earth formed, long before the Sun ignited, long before life emerged. To understand what truly lies at the center of the Milky Way, astronomers would have to do something unusual. They would have to observe something they could not see by watching everything around it. Only then could the darkness at the heart of our galaxy finally be understood. The breakthrough came from watching the stars themselves. If something massive and invisible occupied the galactic center, then the stars nearby would reveal it. They would orbit it. Their motion would trace out the shape of the gravitational field. Their speeds would tell us what they were orbiting around. But observing individual stars in the galactic center required technology that didn't exist in the early days of radio astronomy. The region is crowded, millions of stars packed into a small volume of space. From our vantage point, 26,000 light-years away, separating individual stars from this dense backdrop seemed nearly impossible. The dust remained a problem too, blocking visible light and blurring our view. Infrared astronomy changed everything. Infrared light, with wavelengths longer than visible light but shorter than radio waves, could penetrate the dust. And new instruments equipped with adaptive optics to correct for atmospheric distortion could resolve individual stars even in that crowded environment. By the 1990s, astronomers had the tools they needed. They could identify specific stars near Sagittarius A star. They could track those stars over time. They could measure where each star was year after year and watch as they moved. What they saw was extraordinary. The stars weren't drifting slowly through space. They were racing, whipping around the galactic center at speeds that seemed impossible. These weren't the gentle orbits we're familiar with in our solar system. These were tight, fast, violent ellipses. Stars completing full orbits in mere decades. Stars moving so fast that their motion was visible on human timescales. One star in particular captured astronomers' attention. They designated it S2. A bright blue star, young and massive, orbiting closer to Sagittarius A star than most others. Teams of astronomers began tracking it in the mid-1990s. They photographed its position every few months. They watched it move against the background stars. They traced its path through space. S2 follows an elliptical orbit, like a comet around the Sun, but on a far more extreme scale. Its closest approach brings it within about 13 billion miles of Sagittarius A star. That sounds like a vast distance, but in cosmic terms, it's intimate. That's roughly the distance from our Sun to the outer edge of our solar system. At this closest point, S2 reaches staggering velocities. It moves at roughly 5% of the speed of light. That's more than 15 million miles per hour. For a star, an object containing the mass of multiple suns, to reach such speeds requires extraordinary gravitational force. The orbit takes about 16 years to complete. Astronomers have now watched S2 complete more than one full orbit. They've tracked its motion through perihelion, the closest approach, and watched it swing back out into the farther reaches of its elliptical path. Every observation confirmed the same pattern. Every measurement revealed the same orbital characteristics. S2 was orbiting something massive, something compact, something invisible. Other stars showed similar behavior. S62, discovered more recently, orbits even closer. Its orbital period is less than 10 years. At closest approach, it moves even faster than S2, reaching nearly 8% of the speed of light. Dozens of other stars trace their own paths through this region, each one responding to the same gravitational influence. Each one orbiting the same central point. The physics is straightforward. When an object orbits, its speed depends on two things: the mass of what it's orbiting and the distance from that mass. The closer you are, the faster you must move to maintain orbit. The more massive the central object, the faster the orbital speed at any given distance. By measuring how fast these stars move and knowing how far they are from Sagittarius A star, astronomers could calculate the mass of whatever they were orbiting. The calculations revealed something stunning. The central object had to contain approximately 4 million times the mass of our Sun. 4 million suns worth of matter, compressed into a region smaller than our solar system. Nothing in our everyday catalogue of cosmic objects fit these parameters. A cluster of stars couldn't be that compact. Even if you packed 4 million stars into that small space, they would collide and merge within a short time. The region would blaze with the light of stellar collisions. But no such light existed. The center remained dark. A single giant star. Impossible, no star can be that massive. Stars have an upper limit determined by their own radiation pressure. Beyond a certain mass, a star would blow itself apart. And even if such a star could exist, it would be the brightest object in the galaxy. We would see it easily, but we saw nothing. The observations left only one possibility. Only one type of object could contain 4 million solar masses in such a small region, while remaining completely invisible. A black hole. Not just any black hole, but a supermassive black hole. An object so massive, so dense that it warps space-time into a trap from which not even light can escape. The orbiting stars provided proof. Their motion was evidence. For decades, astronomers tracked these stellar dancers, watching them sweep through their gravitational ballet, mapping the invisible partner at the center of their dance. The stars revealed what we could not see directly. They showed us through their motion that something immense and dark occupied the heart of our galaxy. But confirming the existence of something that allows no light to escape would require capturing an image of the very absence of light itself. Photographing a black hole presents a unique challenge. You're trying to capture an image of something that produces no light, something that exists as pure absence, a void in space-time. The black hole itself would appear as perfect darkness, invisible against the darkness of space. Yet astronomers believed they could photograph one, not by capturing light from the black hole, but by capturing the shadow it casts. Around a black hole, especially one that's feeding, material swirls in a disk. Gas and dust spiral inward, heating up through friction and gravitational compression. This material glows. It emits radiation across many wavelengths. And as light from this glowing material passes near the black hole, the intense gravity bends it, distorts it. Some light curves around the black hole's edge and reaches us. Some light falls inward and vanishes forever. The result is a shadow, a dark circle silhouetted against a bright background, the outline of the event horizon, the point of no return, visible as an absence of light. But capturing this image required an instrument that didn't exist. The black hole at our galactic center, despite its enormous mass, appears small from Earth. 26,000 light-years is a vast distance. Seeing detail at that range demands extreme resolution. A single telescope, even the largest on Earth, couldn't resolve the structure. You would need a telescope the size of Earth itself. Scientists found a solution. Instead of building one enormous telescope, they linked many telescopes together. They used a technique called interferometry. When multiple telescopes observe the same object simultaneously, their signals can be combined. The telescopes act as pieces of one giant instrument. The farther apart they are, the higher the resolution. Place telescopes across the entire planet, and you create a virtual telescope the size of Earth. This was the Event Horizon Telescope project, a collaboration spanning continents, radio dishes in Hawaii, Arizona, Spain, Chile, Mexico, Antarctica. 8 facilities synchronized to observe as one. Each telescope captured radio waves at a specific wavelength, around 1 millimeter. At this wavelength, the galactic center is relatively transparent, and the glowing material around the black hole shines brightly. The observations happened in April of 2017. For several nights, when weather permitted, all 8 telescopes pointed towards the galactic center. They recorded data continuously, enormous amounts of data. So much that it couldn't be transmitted over the internet. Instead, the data was stored on hard drives and physically shipped to central facilities for processing. Scientists then spent years analyzing what they'd captured, combining signals from 8 different locations, accounting for Earth's rotation, correcting for atmospheric effects, building algorithms to reconstruct an image from radio waves. The challenge was immense. Sagittarius A star is dynamic. The hot gas orbiting it moves at significant fractions of light speed. Features in the accretion flow can change in minutes. During the hours of observation, the structure around the black hole was constantly evolving. It was like trying to photograph a subject that won't hold still. Each telescope saw slightly different patterns as the material shifted and flowed. But slowly, through careful analysis, an image emerged. On May 12, 2022, the Event Horizon Telescope team revealed what they had captured: the first image of Sagittarius A star, the first photograph of the black hole at our galaxy's center. The image shows exactly what theory predicted. A ring of bright emission surrounds a dark center. The ring glows orange and yellow in the false color image, though the actual radiation is in radio wavelengths invisible to human eyes. The glow is uneven, brighter in some regions than others, showing the turbulent nature of the material. And at the center, darkness. A circular shadow approximately the size predicted for a black hole of 4 million solar masses. This dark region is larger than the black hole itself. Light rays passing close to the event horizon bend dramatically. Even light from behind the black hole curves around and becomes visible to us. The shadow includes the event horizon, plus a surrounding zone where light is captured. The boundary between light and darkness marks where photons can no longer escape the gravitational pull. It's the edge of the trap, the point where space-time curves so severely that all paths lead inward. The image confirmed decades of theoretical work. Einstein's equations of general relativity, published more than a century ago, predicted exactly this appearance. They predicted how gravity would bend light. They predicted the size of the shadow relative to the mass. They predicted the ring structure. And now, through direct observation, we could see those predictions manifested in reality. The universe behaves as Einstein described. Space-time curves. Mass warps the fabric of space. And around the most extreme masses, that warping creates regions from which nothing escapes. Comparing this image to the earlier image of M87 star, the supermassive black hole in another galaxy, reveals interesting differences. M87 star appears sharper, more stable. Sagittarius A star looks blurred, more dynamic. This reflects their different masses. M87 star is thousands of times more massive. Material orbits it more slowly. The structure remains stable for longer. Sagittarius A star, smaller and less massive, has material orbiting much faster. The accretion flow churns and changes rapidly. Capturing a clear image required sophisticated algorithms to account for this motion. Yet despite the challenges, we have it. A photograph of the darkness at our galaxy's heart. Visual proof of what the orbiting stars already told us. This isn't just a radio source. This isn't just a gravitational anchor. This is a black hole. A region where space-time has collapsed, where gravity has won its ultimate victory over all other forces. This glowing ring around darkness wasn't just light. It was matter in its final moments before crossing a point of no return. The event horizon, the boundary that defines a black hole. It's not a physical surface. Nothing solid exists there, no wall, no barrier you could touch. It's purely a mathematical boundary in space-time. A point of no return. Cross it, and you can never come back. Not with rockets, not with any amount of energy, not even with light itself, the fastest thing in the universe. Once you pass the event horizon, your future contains only one destination. The center, the singularity, whatever lies within. The size of an event horizon depends entirely on mass. More mass means a larger event horizon. The relationship is direct and predictable. For Sagittarius, a star with its 4 million solar masses, the event horizon stretches approximately 12 million miles across. That's the diameter. The distance from one side to the other, it sounds enormous. 12 million miles. But place it in context, and its size becomes more tangible. Mercury, the closest planet to our Sun, orbits at about 36 million miles. The event horizon of Sagittarius, a star, would fit comfortably inside Mercury's orbit. You could fit it roughly 3 times over in that space. Think about that for a moment. 4 million times the mass of our Sun, an amount of matter that would dwarf our entire solar system if spread out as stars, all compressed into a region smaller than one planet's orbit. The density is incomprehensible, not just high density like lead or gold or neutron matter, something beyond material density altogether. At the singularity, if it exists as our equations suggest, all that mass occupies a point of zero volume, infinite density. A concept that breaks our mathematics. A regime where the laws of physics as we know them cease to function. But we're not discussing the singularity. We're discussing the event horizon, the boundary around it. And at this boundary, space-time curves so dramatically that it changes the very nature of direction. Inside the event horizon, all directions point inward. Up, down, left, right, forward, backward. Every possible path leads to the center. You can point your spacecraft outward. You can fire your engines at maximum thrust. You can travel in what you perceive as the exit direction. But space-time itself flows inward faster than you can move through it. You're not pulled toward the center by a force, not in the conventional sense. The geometry itself has changed. The center is the only future that exists. Time behaves strangely near an event horizon. General relativity tells us that time flows differently in different gravitational fields. Clocks run slower in stronger gravity. Near the event horizon, where gravity reaches extreme values, time dilation becomes severe. An observer watching from a safe distance would see anything approaching the horizon appear to slow down. A falling object would seem to take forever to cross the boundary. Its light would redshift, becoming dimmer and redder, stretching toward infinite wavelength as it approached the edge. From the outside, the crossing appears to take infinite time. But for the falling object, for the astronaut hypothetically descending toward the event horizon, the experience differs entirely. Their clock runs normally from their perspective. They would cross the horizon in finite time. They might not even notice the crossing. No physical sensation marks the moment of no return. No warning sign appears. The space around them would look distorted, certainly. Light from the outside universe would appear compressed into a shrinking region ahead. Behind them, darkness would grow. But the crossing itself? Smooth, uneventful. Only afterward would they realize their fate. Only after crossing would every direction lead inward. The tidal forces present another concern. Gravity grows stronger closer to any massive object. Your feet, closer to Earth than your head, feel slightly more gravitational pull than your head does. This difference is small, negligible in everyday life. But near a black hole, this gradient becomes extreme. The difference in gravitational pull between your feet and your head, if you fell feet first toward the event horizon, would become enormous. Stretching forces would grow. You would be pulled apart lengthwise while compressed from the sides. Scientists call this spaghettification. a grim but accurate term. For Sagittarius, a star with its large event horizon, the tidal forces at the boundary are actually manageable. You could, in theory, cross the event horizon intact. You wouldn't be ripped apart at the moment of crossing. The event horizon is far enough from the singularity that the tidal gradient remains survivable. For smaller black holes, stellar mass black holes with event horizons measured in miles rather than millions of miles, the tidal forces would destroy you long before you reached the boundary. But for supermassive black holes, the crossing might be gentle, at least at first. Deeper inside, closer to the singularity, the tidal forces would eventually dominate. But at the horizon itself, you might survive the crossing, even if you could never return. What lies beyond the event horizon remains unknown. Not unknown because we lack observations, though we do. Unknown because the physics breaks down. Our equations produce infinities. Our theories encounter boundaries they cannot cross. General relativity tells us matter collapses to a singularity. Quantum mechanics suggests this might not be precisely true. The combination of quantum effects and extreme gravity may produce something different. A region of extreme density, yes, but perhaps not infinite density. Perhaps not a point of zero size. But we have no complete theory of quantum gravity. We cannot predict with confidence what exists at the center. We can only describe what we observe from outside. The event horizon as a boundary, the shadow it casts, the way it traps light and matter, the influence it exerts on space-time around it. Beyond that boundary, information does not escape. Light does not return. We can theorize, we can calculate, but we cannot know. While nothing can escape from within, the space just outside this boundary hosts some of the universe's most violent phenomena. Material doesn't fall straight into a black hole. It spirals. Like water circling a drain, matter approaching Sagittarius. A star carries angular momentum. It orbits, and as it orbits, it gradually loses energy and drifts inward, forming a disk around the black hole. An accretion disk, a swirling structure of gas and dust trapped in the final stages before crossing the event horizon. This material comes from various sources. Stars in the galactic center shed mass through stellar winds. Normal, continuous outflows of particles that all stars produce. Some stars venture too close to the black hole and are disrupted entirely, torn apart by tidal forces, their matter scattered into orbits. Gas clouds drift through the region, captured by the immense gravity. Over time, this material accumulates. It settles into a rotating disk, constrained by physics to orbit in roughly the same plane. The disk rotates rapidly. Material close to the event horizon moves at significant fractions of light speed. We've seen this in the orbits of stars, and the gas moves even faster, orbiting at smaller radii. As the disk rotates, different layers move at different speeds. The inner regions orbit faster than the outer regions. This creates friction. Adjacent layers of gas rub against each other, generating heat through viscosity. Not friction in the mechanical sense, not like rubbing your hands together. This is friction at a plasma level, where magnetic fields and turbulent flows transfer energy between layers. The heat generated is extraordinary. Friction converts orbital energy into thermal energy. The gas heats up. Temperatures climb into the millions of degrees. At these temperatures, matter doesn't behave like normal gas. Electrons strip away from atoms. The material becomes plasma, a state where particles move freely, unbound to atomic nuclei, and hot plasma radiates. It emits energy across the electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays. The accretion disk glows. Most of the emission we detect from Sagittarius A star comes from this glowing material, not from the black hole itself, which remains dark, but from the matter spiraling toward it, heating up in its final approach. The radio waves we first detected in the 1970s. They come from the accretion flow. The X-rays we observe, generated by the hot plasma close to the event horizon. The infrared glow visible through the dust. Radiation from the disk. Yet Sagittarius A star is surprisingly quiet. For a black hole of its mass, it should shine much brighter. It should consume matter more aggressively. Compare it to actively feeding black holes in other galaxies, and the difference is stark. Some supermassive black holes are surrounded by brilliant disks, outshining all the stars in their host galaxies combined. They produce jets that extend thousands of light years. They blast radiation across the universe. Sagittarius A star does none of this. It's dim, faint, almost dormant. The feeding rate explains this. Sagittarius A star is essentially starving. Very little material reaches it. The accretion flow is sparse, tenuous. Estimates suggest the black hole accretes less than the mass of Earth per year. That might sound like a lot, an entire planet's worth of matter. But spread over a year for an object of 4 million solar masses, it's negligible. The black hole should be capable of consuming much more. The lack of available material limits its luminosity. Why so little food? The galactic center doesn't lack matter entirely. Stars orbit there, gas clouds exist. But most material has too much angular momentum to fall directly inward. It orbits stably, never quite reaching the black hole. The material that does accrete trickles in slowly. Conditions aren't favorable for rapid feeding. Unlike galaxies where streams of gas pour toward the center, our galactic core is relatively calm. Sagittarius A star sits in a state of semi-starvation, glowing faintly, accreting slowly. The accretion flow isn't smooth or steady, it varies. Sometimes the brightness increases suddenly. Flares appear. The X-ray emission spikes. These flares can be dramatic, brightening by factors of several times the baseline level. Then, over hours, the emission fades back to normal. Astronomers observe these flares regularly. They're unpredictable. Some result from clumps of material in the accretion flow. Hotspots that rotate into view, brighten, then rotate away or disperse. Others might be magnetic reconnection events where tangled magnetic field lines suddenly snap and release energy. Magnetic fields thread through the accretion disk. Charged particles spiral along field lines. The rotation of the disk twists these fields into complex structures. Sometimes the fields become so twisted that they release stored magnetic energy explosively. These events heat the plasma, accelerate particles, and produce bursts of radiation. The variability we see from Sagittarius A star reflects this turbulent environment. The disk is not a calm, uniform structure. It's dynamic, chaotic, constantly changing. Some accretion disks launch jets, powerful streams of matter and energy shot outward along the rotation axis. These jets form when magnetic fields channel material away from the black hole before it crosses the event horizon. The exact mechanism remains debated, but observations show jets emerging from many accreting black holes. Sagittarius A star shows hints of this. Weak outflows, faint structures that might be jet-like, but nothing approaching the dramatic jets seen around more actively feeding black holes. Again, the low accretion rate limits the phenomena. With so little material available, the magnetic fields cannot launch powerful jets. The outflows remain weak, barely detectable. The accretion system represents a balance: material spiraling inward, energy radiating outward, magnetic fields channeling flows, all occurring in the intense gravitational field just outside the event horizon. This is matter's final act before vanishing from our universe. These photons we detect, this radiation we measure, these are the last signals from particles about to cross the point of no return. This relatively peaceful present stands in stark contrast to violent episodes from the black hole's past. Sagittarius, a star, is quiet now. But it wasn't always. Evidence scattered across the galaxy tells a different story. A story of violent outbursts, of energetic eruptions that reshaped the space around our galactic center. The black hole we observe today, calmly accreting small amounts of material, is only one face of a phenomenon that can become dramatically more active. The most striking evidence comes from structures called the Fermi bubbles, named after the Fermi Gamma Ray Space Telescope that discovered them in 2010. These are enormous regions of high-energy radiation extending above and below the galactic plane. Imagine two vast lobes, one reaching upward from the galactic center, one reaching downward. Each stretches roughly 25,000 light-years from the center. Together, they span about 50,000 light-years. That's roughly half the diameter of our entire galaxy. These bubbles glow in gamma rays, the highest energy form of electromagnetic radiation. They mark regions where something energized the gas, accelerating particles to extreme velocities. The edges are fairly sharp, suggesting a defined event created them. Not a gradual process, but something sudden, something powerful. And the most likely source sits at the center: Sagittarius A star. The leading explanation involves a period of intense feeding. At some point in the past, a large amount of material fell towards the black hole. Perhaps a massive gas cloud wandered too close. Perhaps multiple stars were disrupted in quick succession. Perhaps a denser region of the galactic disk passed through the center. Whatever the source, the black hole suddenly had abundant fuel. The accretion rate increased dramatically. The disk brightened. Energy poured outward. When a black hole feeds actively, it doesn't just pull matter inward, it drives matter outward too. Powerful winds blow from the accretion disk. Magnetic fields launch jets along the rotation axis. These outflows carry enormous energy. They plow into the surrounding gas, heating it, pushing it away from the galactic center. Over time, these driven flows create bubbles, cavities carved into the interstellar medium by the pressure of the outburst. The timescale appears to be several million years ago. Dating such events is difficult. We can't carbon date cosmic structures, but astronomers can estimate based on the bubble's size and the velocity of the gas within them. The gas moves at roughly 1,000 miles per second. Given the distance it traveled, the outburst likely occurred between 2 and 4 million years ago. In cosmic terms, this is recent. In human terms, this happened when our ancestors were already walking upright on Earth. The Australopithecines were alive when Sagittarius A star last roared. Other evidence supports past activity. X-ray observations reveal clouds near the galactic center that glow unexpectedly. These molecular clouds, dense regions of gas and dust, shine in X-rays. But molecular clouds are cold. They shouldn't produce X-rays on their own. The explanation involves light echoes. The clouds are reflecting X-rays that passed through them long ago. X-rays from Sagittarius, a star emitted during a past bright phase, illuminated these clouds. We see that illumination now reflected toward us, revealing the black hole's past luminosity. These echoes let us reconstruct Sagittarius A star's variability. By observing different clouds at different distances, we see reflections from different times. It's like seeing multiple photographs of the same event from different angles. The black hole's brightness has fluctuated over recent centuries, sometimes brightening by factors of millions compared to its current state, sometimes dimming again, a cycle of feeding and quiescence. The X-ray echoes provide a historical record, written in the reflected light from molecular clouds. The cycle likely continues. Sagittarius, a star, will feed again. Right now, it's quiet because material isn't readily available, but the galactic center is a dynamic place. Stars orbit, gas clouds drift. Eventually, something will wander too close. A star will be disrupted, a gas cloud will fall inward, and the accretion rate will spike. The black hole will brighten. It might launch jets again. It might drive new outflows. We don't know when this will happen. It could be thousands of years from now. Could be millions. Predicting the feeding schedule of a black hole isn't possible with current observations. There are candidates. Astronomers have identified gas clouds on trajectories that will bring them close to Sagittarius A star. One cloud, designated G2, passed near the black hole in 2014. Expectations were high. Some thought the cloud would be torn apart, feeding the black hole, triggering an outburst. But G2 survived. It stretched slightly, but remained largely intact. Perhaps it wasn't just a cloud. Perhaps it contained a star at its core, providing structure. Or perhaps the tidal forces weren't as disruptive as predicted. Either way, the anticipated feast didn't occur. Sagittarius, a star, remained quiet, but other clouds exist. Other objects orbit nearby. Eventually, one will be disrupted. Eventually, the conditions will align for increased feed-in, and when that happens, the black hole will awaken. It will brighten. It will push against the surrounding space. And perhaps, millions of years later, future astronomers will observe new structures, new bubbles, new evidence of this era's outburst. The black hole's history is written in the structures around it. The Fermi bubbles speak of past violence. The X-ray echoes reveal fluctuating brightness. The current quiescence is just one phase in a long cycle. Sagittarius, a star, has been active before. It will be active again. The monster at our galaxy's heart sleeps lightly. Understanding this singular object at our galaxy's heart reveals something profound about the architecture of the cosmos itself. Sagittarius. A star isn't just an object that happens to sit at our galaxy's center. It's the reason the center exists where it does. The gravitational anchor around which everything else orbits. 4 million solar masses don't just occupy space. They shape it. They define it. The galaxy arranged itself around this mass, or perhaps the mass grew within the galaxy and the two evolved together. Either way, they're inseparable now. The structure of the Milky Way, the distribution of its stars, the motion of everything within it, all relate back to that central presence. Our Sun orbits this point. We orbit at a distance of about 26,000 light years, moving at roughly 500,000 miles per hour. At that velocity, completing one full orbit takes approximately 230 million years. That's a galactic year. Since our solar system formed roughly 4.5 billion years ago, we've completed about 20 orbits, 20 trips around the galaxy, 20 circumnavigations of Sagittarius A star. Every star in the Milky Way follows a similar path. Some orbit closer, completing their circuits faster. Some orbit farther out, taking longer. But all respond to the gravitational field established primarily by the collective mass of the galaxy, with the supermassive black hole marking the center of that distribution. The black hole itself, 4 million solar masses, represents only a tiny fraction of the galaxy's total mass. The Milky Way contains hundreds of billions of stars. Dark matter adds even more mass. The black hole is a small component by mass, but by position, by concentration, it defines the center. Astronomers have discovered a curious relationship between galaxies and their central black holes. Nearly every large galaxy appears to host a supermassive black hole at its core. And the mass of that black hole correlates with properties of the galaxy itself. Bigger galaxies tend to have more massive black holes. The relationship isn't perfect, but it's consistent enough to suggest a connection. The black hole's mass often equals about 1/10 of the bulge mass, the central concentration of stars. This ratio holds across galaxies of vastly different sizes. This correlation raises questions. Did the black hole form first and shape the galaxy around it? Did the galaxy form first and create the conditions for the black hole to grow? Or did they grow together, influencing each other throughout cosmic history? Current evidence suggests the last option, co-evolution. The black hole and galaxy developing in tandem, each affecting the other's growth. The mechanism likely involves feedback. When a supermassive black hole feeds actively, it releases enormous energy. This energy drives winds and jets that push gas out of the galactic core. Gas pushed away from the center can't form new stars. The black hole, by feeding, regulates star formation in its host galaxy. If star formation proceeds too rapidly, more material eventually feeds the black hole, which then drives stronger outflows, suppressing further star formation. A self-regulating cycle. The black hole acts as a thermostat for its galaxy. This has profound implications. The properties of galaxies across the universe, the rate at which they form stars, the distribution of matter within them, all connect to the supermassive black holes at their centers. Sagittarius A star isn't just a curiosity at our galaxy's heart. It's part of a universal pattern, a feature of galactic architecture that appears throughout the cosmos. Most large galaxies have them. Some have black holes far more massive than ours. The black hole at the center of M87, famously photographed before Sagittarius A star, contains several billion solar masses. Others are even larger. Some black holes approach tens of billions of solar masses. Sagittarius A star at 4 million solar masses is actually relatively modest, but it's ours. It's the supermassive black hole that anchors our cosmic neighborhood. We exist because of this architecture, not directly. The black hole didn't create our sun or our planet, but the processes that led to galactic structure, the regulation of star formation, the distribution of matter, all involve the black hole's influence over billions of years. Our solar system formed in a disk of gas and dust, created by earlier generations of stars. Those stars formed in a galaxy shaped by its central black hole. We are products of this long chain of cosmic influence. Our position in the galaxy matters too. We orbit far from the center, far from the intense radiation, the tidal forces, the disruptions common in the galactic core. Life as we know it probably couldn't exist close to Sagittarius A star. The environment is too energetic, too chaotic. Stars pass close to each other. Orbits are perturbed. Planets would be stripped away. Radiation would sterilize surfaces. But out here in the galactic suburbs, conditions are calmer. We have the stability needed for life to emerge and persist. The black hole will outlive us. Our sun will die in about 5 billion years. It will swell into a red giant, consume the inner planets, then shed its outer layers and fade to a white dwarf. Long after that, after our sun has cooled to darkness, Sagittarius A star will remain. Black holes don't die easily. They can evaporate through Hawking radiation, but for a black hole of 4 million solar masses, that process takes unimaginably long. Longer than the current age of the universe by factors too large to comprehend. For all practical purposes, Sagittarius A star is eternal. It has been there since the early universe. It grew as our galaxy grew. It witnessed the formation of hundreds of billions of stars. It will witness their deaths. It will persist through the deep future, long after the last star has burned out. Long after galaxies have drifted so far apart that the night sky goes dark. In that distant era in the cold and empty universe, Sagittarius A star will still exist. A monument to gravity, a reminder of the galaxy that once swirled around it. We're here briefly in a galaxy built around this invisible anchor. Looking toward Sagittarius, toward the heart of our cosmic home, we're looking toward the organizing principle of everything we know. The monster at the center, silent, patient, eternal.